Now the first thing is I'm going to just quickly do the basis thing, comparison of bases. You've got comparison of bases. That's the first thing. Now, when you talk about bases, nitrogen has a lone pair, and lone pairs they like to gain H+1 ions. So you've got NH and R, that's an amide. Then you've got another one which is a normal amine. A normal amine is a strong base. Let's talk about phenyl amine, which is a benzene. With an NH2 group. So it's a benzene with NH2 group. And then you've got ammonia, that's like a reference point for comparison because ammonia is a base. And you've got alkylamines. Alkylamines are carbon chains, like a CH3 and a CH2 with an NH2. Now, each one of these nitrogens has these lone pairs. It's got, I mean, this one has got a lone pair. This N over here has got a lone pair. This N over here has lone pairs, and this N over here also has lone pairs. So they all kind of have these lone pairs. And these lone pairs attract H+1 ions. So whenever you have an H+1 around, the H+1 is going to be attracted to these, it's going to be attracted to these lone pairs. So in all cases, these H+1s are going to be attracted to these lone pairs. And the lone pairs are going to get attracted to, or vice versa, the other way around. The lone pairs are going to get attracted to the H+1 ions. But anyway, so these are all basic. They accept, what's a base? Base accepts H positive ions. So it accepts these H+1 ions. Now the first one is not basic. It's not going to do that. So in the first one, that's not going to happen. It's not basic. So the H is not going to get attracted to this. Okay, let's put a crossover here. It's not going to get attracted to it. And as you move to the right, the basicity increases. So this one is a relatively strong base. And remember, speaking relatively, they're all weak bases in reality, but relatively speaking, that's a strong base. So there's a gradual transition that happens when you move from left to right, and that is the strength of bases, it increases. So the question is, why is the first one not basic? The reason is, the reason for the first one is, why is it not basic? Because what happens to the lone pair? The lone pair gets pulled towards this oxygen over here. It's a very electronegative oxygen. So there's a pi electron cloud over here. The lone pairs over here get attracted to this oxygen, and they're not available for the H+1. So the H+1 is not going to get attracted to them because you don't have the lone pairs over there. The lone pairs mix with the double bond over here and they get attracted to the oxygen. So in this case, what you're going to write it is, why is it not basic? Because oxygen in serial bond O is very electronegative. So it's highly electronegative. And because of that, the lone pairs on N gets withdrawn, or lone pair on N overlaps with the pi electron cloud in the double bond. and is not available. Is this clear, the first one? Roberta, is
Yes,
this clear?
sir.
Yes, sir.
So what about the next one? In the next one, you have an electron withdrawing effect, but now it's slighter because the lone pairs, they overlap with benzene's pi electron cloud. But this time, benzene is not that electronegative. So this one is relatively a weak base. I mean, it is basic, but it's a weak one. So this one is a weak base, and you're going to write the same thing, kind of, that the lone pair overlaps with benzene's pi electron cloud. But this time the overlapping is not complete. That, like, the lone pair is still there, but some of it is still there. So it will still attract the H+1, but not that strongly. So lone pair overlaps with benzene's pi electron cloud, and its charge density decreases. So it's still kind of there. It's not fully overlapping with it. So, and its charge density decreases. So there's going to be less attraction for, or weak attraction for H+1 ions. Then you have the last one, like ammonia is a reference. So let's look at the last one. In the last one, that's a strong base. Why? Because relatively a strong base, because alkyl chains have an electron donating effect. So what alkyl chains would do is that they're going to push electron density towards this nitrogen atom, and the lone pair electron density would actually increase. There's going to be a lot more electrons there because the carbon chain is going to push the electron density. So alkyl chains have electron donating effect. So they're going to have electron donating effect. So the charge density on the lone pair as a charge density on the lone pair increases. And you also remember that if you have more alkyl chains, like if you have a tertiary amine, like if you have carbon chains on all sides, it's going to be a stronger base. So it increases, there's going to be more attraction for H+1 ions. So there's going to be more attraction for H+1 ions, and it's going to be a stronger base. So remember, if you have more alkyl chains or bigger alkyl chains, that's even stronger amine. Or a bigger alkyl group. So that's going to lead to an even stronger base. Okay, is this all clear?
Yes, sir.
So now the next part is that's about bases. The next part is that you have got so let's talk about how amines are formed. So formation of amines. So there's several different reactions where amines are formed. One of them we just, one was the nucleophilic substitution reaction of, so reaction number 1, a nucleophilic substitution of halogenoalkanes. Of halogenoalkanes. Now, if you remember, that's an AS reaction. It's SN1, SN2 mechanism, depending on what type of halogenoalkane it is. So the conditions for that reaction are that if you have a halogenoalkane and there's a Cl, what you need to do is you just need to react it with ammonia, which is ethanolic. So it's either ammonia, ethanolic, and reflux. Plus reflux, or you could have ammonia gas at high pressure in a sealed container. In a sealed So you can have it in a sealed container at high pressure and heat. You can heat it. So plus heat is required. So in a sealed container and you heat it, that would give you or yield, it's going to happen. This is what's going to happen, that you'll have. So anyways, you'll have this molecule. The Cl gets replaced by NH2 and it will form an amine. That's it. So that's one way of forming amines, halogenoalkanes. That's what you did in AS. The second method, which is the newer method, is a reduction reaction of the reduction of nitriles. You can do reduction of nitriles and you'll have a nitrile like C triple bond N, that's a nitrile. You reduce it. Reduction means addition of hydrogen. So you can use NaBH4, LiNH4 as reducing agents. You can remember these were your two reducing agents, NaBH4 or LiAlH4. Or you could also use nickel plus H2 gas. You can hydrogenate it. And what will happen is that that this is going to be formed, that the C and the N hydrogens are going to get added to it and it will form an amine. So hydrogens are going to get added to it and it will form an amine eventually. Then there's another reaction, which is number 3, which is reduction of amides. So what if you have an amide, which is basically RC double bond O, NH, and an R. Now, in this case, what will happen is use LiLH4 and the oxygen is lost. So you have NH and hydrogens get added to it. So so this is the only thing that's changing. This red part over here, that's the only thing that's changing. So this part, it changes. Instead of having an oxygen, it turns into an amine. It's just got NH2. Okay, so you've got these three reactions, and then there's a fourth one, which is a reduction of nitrobenzene.
So
Yes.
for the reduction of amides, how is there NH2?
Which one?
Because it's NH only in the example.
Okay, that one is I mean, this one is a secondary amine. Like, remember, an amine could be primary. It can be primary, secondary, or tertiary as well. Like you can have carbon chains on all sides, or you can have one carbon chain with 1,8. So I mean, it's just an N with a carbon chain basically. And if there's room for hydrogen, you're going to add hydrogen to it. Is this point clear?
Yes.
So this is just like a typical amine. It's a secondary amine actually. It's instead of NH2, it's got NH because it's in the middle of the chain. So then you've got a reduction of nitrobenzene. What happens in that case? Nitrobenzene was the benzene. If I can just copy a benzene quickly. So what's a nitrobenzene? Nitrobenzene is that you've got 1 second. So your nitrobenzene was NO2. And you can exactly reduce it in the same way. What will happen is that this entire thing, the oxidants would be lost. And instead of NO2, you'll have NH2. I mean, the H will get added to it. So that's another reduction reaction. So instead of the oxygen, hydrogen atoms are going to get added to it. And the way this is done is you need tin, you need SN. I mean, this is not the nucleophilic substitution SN. This is tin plus concentrated HCl. So remember, these are the 4 reactions where amines are going to be formed. Amide can be reduced, nitriles can be reduced. You can reduce, you can do nucleophilic substitution of halogenoalkanes, and that would also give you amines. So 4 reactions which would all produce amines. Is this all clear?
Yes.
Yes, sir.
Yes.
The next thing is there's a thing called diazonium salts. Diazonium salts and Azo Dyes. Diazonium salts are used to make Azo Dyes. Now, what are Azo Dyes? Azo Dyes are your normal dyes, your paint stuff that's that you usually use in like car paint, etc. I mean, you're painting doors, you're painting. So most of the paints that you use, okay. So now paints are kind of a tricky thing to make. The reason paints are tricky is because chemicals are very reactive. I mean, most of the time chemicals are really reactive. So if you have, I mean, the difference between a good quality paint and a bad quality paint is you don't want the paint to be reactive. You want it to be really inert. Like if you paint something red, you want it to remain red after 10 years. You don't want it to get washed away with water. You don't want it to change color or react with the air. So making paints is kind of tricky. like car paints, the paint has to be really, really stable. It has to be really unreactive and inert. So Azo dyes are kind of those things. They're very stable dyes. They don't get affected by sunlight. They don't get affected by water, rain, heat, and they don't change color. So I mean, you don't see your car changing color or fading. Its paint fade. I mean, it does fade, but it doesn't happen very quickly. So so you make Azo dyes. How do you make Azo dyes? What you do is, this is the reaction pathway of making an Azo dye. So I'll just copy the benzene first, and let's start with this thing. I mean, basically, okay, what I can do is I can add another path to it. I mean, okay, let's start at this point. Forget the previous path. We already know this. Like, we know how to make an amine. So we start off with an amine, and you just need to know the reaction paths. Like, you have an amine, you take an amine, and what you do is you heat it. I mean, you don't actually heat it, you react it with an NO2 plus HCl. And the temperature is kept around or less than 10 degrees centigrade. So when you do this reaction, this amine, it turns into this very unstable compound known as a diazonium ion. I mean, the H is lost. And instead, what you get is something like this. It's N triple bond N. And it's got a charge of +1. So this, and if it's positive ion, there might be a Cl which would be negative as well. So it's often referred to as, I mean, you can write it as C6H5, N2 plus, and Cl -1. So that's a diazonium salt, and this one is the diazonium ion. Now, it's a very unstable ion. It's a very unstable ion. A little bit of heat will decompose it. Like, if you heat it very slightly, even in water, it's going to decompose to form a phenol. So don't heat it. The temperature has to be kept less than 10 degrees centigrade. Heat and water. And what I mean by heat is, if temperature increases to greater than 10 degrees centigrade, the whole molecule is going to decompose, and it would eventually form what it will form, a phenol. So it's going to decompose to form a phenol molecule, and maybe some NH4 +1 ions, etc. So the thing is, don't heat it. It's going to decompose to a phenol. So what you need is, you want this stable ion to be this very unstable ion. You want this unstable ion. So this is it. It doesn't I mean, it is decomposition, but it's hydrolysis. It reacts with water.
Sir, if it has a triple bond, so how is it unstable, and yeah, why does it require so less heat to break a bond?
The thing is, it's got a positive charge. It's got a very strong positive charge. So water, I mean, it's got a triple bond, but it's very electron deficient as well at the same time. So water molecules, the lone pairs are going to get attracted to this N over here. Okay, is this clear?
Okay. Yeah, yes, sir.
As a Baki, the details are not necessary. I mean, the mechanism is not required. What happens, but it's very unstable. It's going to decompose very quickly in the presence of water, and water is kind of everywhere. In most solutions are water. So you want this diazonium ion. You want to keep this diazonium ion. The diazonium ion then goes on to react with an activated benzene. The diazonamine acts as an electrophile. Because it's got a strong positive charge. And it reacts with an activated benzene. So let's copy that diazonamine again. So it's got a positive charge, so it's going to be attracted to electrons in the benzene electron cloud. So here's your diazonamine. Here's a benzene. Now remember, you don't want a normal benzene. You want a benzene that has a high electron density. So which is why what you'll do is you'll remember there were 3 electron donating groups. But one was a carbon chain. One was an OH. The OH is fine because it's got lone pairs, or it could be NH2 as well because, or it's going to be NH2 because NH2 also has these lone pairs. But anyways, if you have OH, the lone pairs of O from OH is going to overlap with benzene's pi electron cloud, and the electron cloud density would increase at positions 2, 4, and 6. Okay, we studied 3 electron donating groups, or 2, 4, 6 donating groups. You had an OH, you had an NH2, they got lone pairs. The lone pairs would mix with the benzene electron cloud, and the electron density would become higher. There was alkyl chains as well, carbon chains, but the electron donating ability wasn't that great. It was there, but not that great. So we're going to keep that to the side. We're not going to talk about them. Anyways, the electrons are going to be attracted by the diazonamines. And this is what's going to happen. That the 2 benzenes are going to get connected to each other. So the 2 benzenes will eventually join up, and they're going to join up at this position. Like the N triple bond N+1 is going to be pulled closer to the highly active benzene. And this N will connect with the benzene over here. The positive charge, it's going to get electrons from the benzene. And this molecule would be formed. Again, it's making 3 bonds, and this N is also making 3 bonds. So that's stable now. And we can ignore this. Anyway, so this is what is happening, and that's your Azo group. This thing over here is known as an Azo group. This entire thing is known as the Azo dye. This is the paint stuff that you use on everyday basis. I mean, it can have a lot of variations because I mean, this is one of the basic version of it. I mean, there are going to be groups attached to it. There would be groups attached over here as well. So, but this is the basic version of what an Azo dye looks like. And the conditions for the reaction are you need alkaline conditions, any which aqueous. You want any which aqueous, that's your conditions for this reaction. Pretty much that's the only condition. So that's how diazonamines are produced. An Azo dye is produced. First thing, at a temperature very low, you make a diazonamine, and the second thing is the diazonamine is reacted with an activated benzene. Has to be an activated benzene, this one. Is this clear?
Yes, sir.
And remember, you're going to get a lot of questions on this. So I'm just going to draw, I'm just going to show you formulas of Azo dyes. So just to, remember when they show you these alternating double bonds, that's a benzene. So just to give you an overview, of what kind of, I mean, look at, I mean, where's the Azo Dye? Just a second. I mean, let's talk about this one. So here are some Azo Dyes. What you can see over here is there's always one of the benzene is going to be activated, like you got an OH over here. And the other one is not going to be that active. Probably similar over here. There's one with OH. So remember the benzene, there could be many different groups that could be attached to it. So let's see. I mean, you can have a look at this one. Same thing. There's an N double bond in. One of the benzene is activated, so it's got an OH group. The other one is not that active. So that's how Azo Dyes are formed. So you'll have all types of different Azo Dyes. This one is an Azo Dye as well. Like you got a double bond over here. One of the benzenes is active. It's got N with lone pairs. The lone pairs are going to mix, and the electron density over here is higher. The other one is a normal benzene, and there are two Azo groups over here. This one is the activated benzene. This one is the normal benzene. So all kinds of dyes and the colors. And here's a Wikipedia page of anyways, these are most of the colors that you see around you. They're non-toxic, and I mean they're kind of overall non-reactive, so that's kind of inert as well. And they're very stable compounds. So they use it for metals, that's your car paints, etc. Use it in textile, etc. I mean, pretty much everywhere. So is this clear? Where's the port? Is this clear?
Sir, with heat, with heat and water, the paint will fade away?
No, not the paint. The diazonium ion is unstable. Remember, once the Azo Dye is formed, there is no diazonium ion. That's gone. I mean,
Okay.
I mean, this is stable. The diazonium ion got stable by pulling electrons from the neighboring benzene, and it ended up forming this Azo group. So it eventually became stable now. So before it was just one step before it was very unstable. Now it's stable. I said the other thing is, the tricky part is that if you have an Azo Dye, the tricky part is figuring out what the original reactants are. Because I mean, let's copy the same molecule. I mean, it's not that tricky, but people get confused with this. So let's say we have this molecule. Now the trouble is that, and let's say I make a variation of this, like there was a CH3 carbon chain over here and a CH3 chain over here. But it's the same, it's just a different version of the same dye. I might have a different color because I've added some groups to it. And yep, so, and let's say this is a carboxylic acid. I said, but anyways, the basic structure is the same. The red one structure, that's exactly the same. Now the difficult part is, or the tricky part is, how do you find the original elements, the original compound that actually made this up? So the only confusion is, remember, think of this in reverse. You had an N double bond N in the middle, that's your Azo group. This one was the diazonium ion, the other one was just a simple benzene, right? So you have to decide one thing, and that one thing is, okay, where would this go? Would it, like, originally, was it attached on the left side or on this benzene, or was it attached on this benzene? Okay, that's kind of hard to figure out. Like if they didn't show you the reactants and they're asking you for the reactants, you kind of get confused, like where would the N triple bond N+1 be? Would it be with this one or would it be with this one? So the easy answer to this is that if you know the structure of the compound and you want to figure out the original reactants, then this thing is going to be going to the non-active benzene. The N triple bond N+1 is with the non-active benzene, not with the one that's got an OH or an NH2 with it. Is this point clear?
Yes, sir.
So like if I want to draw this one, the only issue I have is, I mean, I can draw the original molecules easily. So there's going to be this one. Okay, that's one part. And there is this other one. And the only trouble I have is who gets the N triple? Which one was the diazoniamine? This one or this one? So if this is the active benzene, because it's got an OH, the N triple bond N+1 was probably with this one. Okay, that's going to go to the one that's the inactive one. So that's the only thing that you should remember. Is this clear?
Yes.
Yes, sir.
Yes.
Okay, I mean, doing the other one is going from the reactants to products, that's easy. Going back from the products to the reactants and figuring out the reactants, slightly difficult. Just figure out that the N, I mean, there should be a double bond here. I don't know where it went, but so just remember that you have to figure out which one was the diazoniamine, this one or this one. So one of them would be active, the other one would be the diazoniamine. So just remember that. So okay, let's continue next time and we'll try and cover proteins and other nitrogen compounds. Okay, we're pretty much done with nitrogen compounds. All we have to do now is study proteins, that's it. So, okay, everyone.
So please send the notes.
The link to the board? Okay, I'm sending it here.
Okay, sir.
Sir, when will the A2 syllabus will complete?
I mean, for organic, we're almost done. We'll just be
Okay.
left. We'll just be left with transition metals, and I mean, we can do the NMR in a bit more detail after that. Okay.
How long will it take?
The whole. Yeah.
Transition metals it's not going to take that long. Probably this month. Okay.
Okay, sir.
Okay.
Okay, thank you.
Okay, take care. Allah Hafiz.